So good morning once again. So in today's lecture, it will be very light. We will just see how to write a simple C program. We don't even try to understand what is going in that program, but we will understand how we enter a C program and what is the process that we have to follow to execute a program. I hope the concepts discussed in the last two classes are clear to you. I would like to kind of emphasize again that there will be many questions to you, okay, naturally. And, all those questions, they will be answered. No, some questions may be answered within this course. Some questions, no, in some other courses. You know, so it's a process. Okay, all your questions. Some of the questions we have to keep them aside. Like some questions we will. So some questions we will. They may be answered. They will be answered in computer systems organization course. Some questions will be answered in operating systems course. Some questions in later on in a course on compilers. So all you'll get very good understanding over your program of study here, all of you. All right. So a very simplistic view, a very high level view of a program, if you see, there is so a program takes an input. Okay, you have a program. So a program takes input and it does some computations on the input and then generates output. Say program does it takes some input and then it does some computations on the input and then generates output. So examples of of input and output pairs are like, for example, you can have a program which converts color to grayscale. So the input is an RGB image. You know, it's in an image there are three components. Your image is a collection of pixels. Like for example, if you have an image, this is your image. Your image is it is represented as a collection of pixels. This is a pixel of an image. And there are three components to this pixel: red, green, and blue components. And this is how we get a color image. But in grayscale image, you will have this. If it's a grayscale image, instead of having three components, you will have only one component, which we call as grayscale. So you can have a program which takes an RGB image and generates a grayscale image. You know, in order to generate a grayscale image, so we can have something like a grayscale pixel G. It can be a combination of, you kind of say, I will take 0.4 times the red pixel plus, let me use the value of the R pixel plus 0.3 times G value plus 0.3 times blue value. Like that, you take some combination of values of the RGB components and you generate a gray scale pixel. And then this is, so if you take a pixel here, if this is your color image and this is your grayscale image, let's say in order to say it is grayscale, let me use, so what color I should use? Okay, I'll use, I don't have a gray color on my zoom. So this is your thing. So every pixel here, it gets mapped to the corresponding pixel in the grayscale. And the way this is a transformation. Okay, so you're transforming these RGB components into a single value, that is a grayscale value. And remember, yesterday we were talking about the fun in programs come when we repeat the same operations again and again and again, same instructions again and again and again on different data. So here, if you see, let's say if there are 1,000 pixels, there are 1,000 rows here and 2,000 rows in this color image. So you have to iterate through these 1,000 into 2,000 pixels, color pixels, and generate this grayscale image with 1,000 into whose dimensions are also 1,000 times 1,000. So what is the important point? The same operation, the same operation, this is the instructions. The same operation is again applied again and again and again on different pixels. Are you all with me on this example? Any questions?
वो कौन? अच्छा वो वाला, तो उससे क्या दिक्कत है?
Just trying to look at the chat box. Just give me 1 minute, guys. I'm just trying to.
वो काट दो ना.
Okay. Since my mic, since I muted my, not muted, no, my speakers, I just completely kept them on low volume, so I am not able to hear the noise in the background. So that's the reason. So there is this question. Just want to clarify again here. The first point is a color image. If you take, just trying to, through an example, we are trying to understand. So the first point. Why am I not able to create a new page? Just give me one moment, yes, there is some issue. I should be able to create a new page on the whiteboard. I'm not able to do that. What is the reason? Okay, I have to clear my drawing. Still not able to. Okay, let me do that. So to recap, so those of you who are a bit lost, so again, I want to set the context here. So the first thing that we have is, so we are trying to think of a program whose input is a color image. Okay, whose input is a color image. You know, how is an image represented? In digitally, how is an image represented? Pixels. It's represented as a bunch of pixels. Okay, so this is, there will be set of rows and there will be some columns. So can you think of your image as a matrix? Can you think of your image as a matrix, right? In fact, you can think of your image, your color image, as three matrices. Red matrix, blue matrix. Your image is a combination of three matrices, just not one matrix. So red, blue, every color image has three components: red, blue, and green, RGB. Or you are fine with this idea that thinking that you can think of your image as a collection of three matrices: red matrix, blue matrix, and green matrix. And you know, so you want to transform this color image. So you just so the way once every pixel has a red component, blue component, and green component, and your image is rendered on the screen based on these RGB values. Based on these RGB values, they are represented separately. Okay, the red component, the red matrix, blue matrix, and green matrix. Think of them; they are separate matrices. So now you want to transform your image. You want to transform your image. You want to write a program. So you want to write a program. So this is your program. So let's call that program as RGB to gray. This is your program. So this program takes as input your color image, which consists of all these three components, and then it maps it into a grayscale image. And this matrix, this is only one matrix. There are no three matrices here. This is your grayscale image matrix. So one super simple way of generating a pixel here, let's say if you look at top left corner of this pixel, so in order to get this pixel, so one simple way of doing it is you just say, let's say this element we are calling it as R00, mathematically speaking, and B00, and G00, 0, 0. And your pixel G, let's say, let me this pixel, you can say G00 is equal to R00 plus B00 plus capital G00 divided by 3. You take the average of these things. And in order to differentiate between gray and green, let's use a different name for this. I will say GR. So you take the average of the RGB components and you generate. Generally, more generally, you can kind of write that the I comma jth pixel here, that is the if you take the ith row and the jth column here somewhere, jth column here, so that would be something like this. This is your ith row and jth column. Let me use this green color to indicate this is the ith row and the jth column. Is obtained by taking Rij plus Bij plus Gij divided by. See, just think of, there are questions on why whether this averaging makes sense or not. The point of this example is not that. Okay, the point of this example is there is some function which takes the RGB components of a pixel and maps it into a grayscale. Are you all with me here? What that function, whether average is the right function or something else is the right function, maybe square of the red pixel plus 2 times blue pixel plus the square root of green pixel, any of those things are possible. It's fine. Okay. So the point of this example is that you have to write a program which in some way takes the I comma j pixels of the red, blue, and green components of the I comma j pixel in the color image and maps it into a grayscale image. And the interesting thing is this function that we are talking here, it needs to be applied repeatedly on all the pixels of the color image so that the whole grayscale image is rendered. So any program, if you see, that program will have an input and the program will have an output. A more complicated, slightly more easier example. Are you all with me here? Shall I proceed? Shall I proceed further? Okay. A slightly more easier example is, you have a program, you want to write a program. So let's call it as sum n. So which takes as input n. This is the input, and the output it generates is sigma I is equal to 0 to sigma I is equal to 1 to n I. So is the grayscale program an example of control transfer? Yeah, and there will be control transfer in the grayscale program for sure. Pretty much in all programs, even in the program that you are seeing right now, you will see that the same instruction is being executed again and again and again. So control transfer will be there pretty much in all the programs that you write, except perhaps that you see in today's class and the next class. Okay, when we talk about extremely simple examples. But apart from that, any program has control transfer. Are you fine with this example? this example program, you want to write a program which takes as input an n and it generates the sum of first n numbers. Or you may want to write a program is prime, okay, which takes as input and it outputs yes if n is prime, and it outputs no if n is composite. So like this, every program that you consider, it has an input, and the program does some kind of computations on the input and it generates output. Can you give me some examples, some more interesting examples you can think of input-output possibilities? Armstrong number, factorial, and Fibonacci, square of a number. Nice. Good. In fact, if you think of leap year, reverse string, in fact, if you think of your calculator, that's what the calculator does, right? So in the calculator, you give some input and you give some operation, and and then it gives the value of the expression you are trying to compute. Yes, square root of a number, all these things are possible. So now let's see, we will see a super simple program. Let me share my screen. You are able to see my whole screen, right? I'm sharing my whole screen so that you can see. This is a Ubuntu machine, and in order to write a program, the first tool that you need to have is you need to have an editor. And in this course, we use the editor Visual Studio Code. Visual Studio Code is a very good editor to write your programs. It is more than an editor. You can do many things with Visual Studio Code. My Visual Studio Code, I opened this after a long time. It is doing some interesting stuff. Okay. So now, you see, I just open a new file. So now a new file is open. And I want to, as soon as I open the file, I want to store, yeah, so I'll create a directory, computer programming. This is too big name. I'll just say CP21A, create. And in this program, so let's say we write, we are naming every C program, the name of the file in which we type in the C program, it should have an extension .c. So that's the reason we have .c, hello.c. All right. So you can even try along with me. Okay, you can open the editor Visual Studio Code. I hope all of you have installed Visual Studio Code. So open the Visual Studio Code and then follow along with me. Or if you don't have Open Studio Code, you can use any other editor, but not Word document or anything like that. Okay, some simple editor you can use. Use some simple text editor, maybe Notepad++ or online C compiler is a workaround. Let's see, onlinegdp.com. Thank you, online. Okay, so you store it in, thank you, David. Hello.c. So once no, I think you have to install it there in so using this. So what happens is in Visual Studio Code, you can install several plugins. Like for example, these extensions. I think this is what we have to use, and search for extensions which support C programming language. Don't write programs in CPP, please write in C. So the name of the file is .c, and you can see here this capital C, so which indicates that the editor recognizes, VS Code recognizes that you are trying to write a C program. Do you want to install recommended extensions for C? Let's see what we have. Yeah. So you should try to install this C++ Microsoft extensions as in the Visual Studio Code. So these extensions are very powerful. So when you make any mistakes, or it gives you auto suggestions, and many nice things will happen once you install these extensions. I also suggest all of you to install this C++ extension. You can search for this extension by pressing this Control Shift X, or this the button here. Are you all with me so far, everyone? Anyone having a trouble? So install extension also. So this is the homework. This you can do it now itself actually. Now we are writing our first C program. So the conventionally we say there is what is called as a hello world program. Don't worry about the syntax. So slowly type in what I am typing in here. Don't copy paste from internet. Okay, first few programs when you type it in, it will be good for you. So hash include stdio.h, and then you say void main. So every C program, it will have you can start this as a baseline code. Every C program, you can start this as a baseline code, and in order to save your program, you should keep saving your program in between. So one simple way is Control S. Okay, it's Control S. Okay, so now you have created your first C program. In Mac, yeah, Command S in Mac, yeah. And then, so we use what is called as an output printf function, and then say write this in hello world, and it ends with a semicolon. So now we have written a C program which consists of one function. Okay, it's a program is divided into a collection of functions. So you use so our program now has only one function which is called as a main function, and you use printf. Don't use cout. Okay, we stick to C because in the all the evaluation, everything it will be in C. Don't use any C++ features. Okay, printf hello world. So now your program is complete. Your program is complete. So when you execute this program, remember we talked about that every program is a collection of instructions and the processor executes the instructions one after another. So when you execute this program, the first instruction of this program is there on line line 5, which is a printf statement. And when that printf statement gets executed, hello world gets printed on the screen. All right. Are you all with me here so far? So one more important thing I want to, so where is this program hello.c got stored? Where is this program hello.c got stored? Where is this program hello.c got stored? Is it stored in the main memory, RAM, or is it stored in the hard disk? It is stored in the hard disk. Right now, we have written a program. I want you to understand this very clearly. That so now I am opening terminal. So this is the terminal. So I created a folder CP21A. So I'm going to CP21A, and and then here, if I do an ls, hello.c is present on the file system. Okay, so it is present on the hard disk. And if I do ls minus al, you will get to see that hello.c program is created at time 10 hours 35 minutes on November 27th. And it has 63, it occupies 63 bytes. The size of that file is 63 bytes. And this program is present on the hard disk, on the file system, not on the main memory. How is this program stored in the hard disk? How is this program stored in the hard disk? This program is stored in the hard disk as a sequence of characters. Just like, English, when you type in an article in English, your English article, it's a sequence of characters. So your program is stored on your hard disk as a sequence of characters. And every character has an encoding, which we call as, so there are different character encoding mechanisms. And one particular character encoding mechanism is called as an ASCII. No, we didn't yet run the program. All I am telling you is this program is stored on the hard disk as a sequence of characters. This program is stored in the hard disk as a sequence of characters. And every character is encoded, because remember, every character is represented using a byte. Okay, so every character is represented. So every character is represented using 8 bits or a byte. So and the encoding mechanism that we use is what is called as an ASCII encoding. This is what is called as an ASCII encoding. And later on, you will see there is also what is called as a Unicode encoding. So, but in ASCII encoding, every character is represented using a byte. Byte is 8 bits. One character, one byte. One character, one byte. One character, one byte. As simple as that. Okay, like for example, A could be represented in the form 1001, 0001. So remember, this is 4 8 bits, right? So yeah, space is also a character. Space is a character, left parenthesis is a character, right parenthesis is a character, the pound symbol or the hash symbol is a character. All these things are characters. Are you all with me so far? So the sequence of bits is stored. The sequence of bits is stored on the hard disk. Remember, when it is stored on the hard disk, each bit is encoded on the magnetic disk of your hard disk. Or if you are storing this on an SSD storage, then then different technology is used to represent one bit. There is this question from Yash: how is space stored? So space also has an encoding. So this is space. Think of this as space. Then space will also have some kind of encoding space. So, and that encoding corresponds to space. Everything has an encoding. Everything is represented as a sequence of bits. So we will talk about the ASCII and the Unicode later. Let's not worry about it in today's lecture. So now if you use this command, file hello.c, your Linux operating system knows, since it is a .c extension file, that it is a C program and it contains ASCII text in it. All right. But this program that we are seeing in the editor, this is a program which we understand. Okay, this is, but the processor does not talk this language. The processor does not talk this language. So we have to translate these instructions, these high-level instructions, into a sequence of low-level instructions, which your processor can understand, which your CPU can understand. So, so here, the intent behind, so as a programmer, you expressed your intent saying that I want to print hello world on the screen, and you expressed your intent using the language rules given by the C programming language, syntactic and semantic rules provided by the C programming language. All right. So now, in order to translate this into a form which your processor can understand, we have to use compiler. So GCC is a compiler which translates C programs. So this is the command that you have to use. There's a different command also you can use. But let's say GCC hello.c -o hello. What it does is it translates these instructions in the hello.c into a form which your processor can understand. Okay. So now the file hello.wo. So now if I do ls -al, where is hello present? Where is the hello present? Is it present in RAM or is it in hard disk? No, hello is not present in the RAM. Hello, you translated hello.c program into a form which the processor can understand, but it is still present on the hard disk. It is still present on the hard disk. I really want all of you to understand these ideas. Okay, so this is hello.c and this is hello, and hello is present on the hard disk. No, the size of the hello, it's 16,000 bytes roughly. Okay, 16,000 bytes of data is present in hello. Are you with me here? Good, doing all right. That you generated hello and hello. No, you. So what we did is very simple, right? So you just compile the program. Yeah, so we'll come to that. Why is it so large? We'll see later. But all we are doing is we are translating hello.c into a sequence of instructions which the processor can understand. Yes, Gnaneshwar got it perfectly right. So we converted the C program into a form which the processor can understand, but we still didn't load the program. That's all. Excellent, Gnaneshwar. You summarized it very nicely. Are you all with me on what Gnaneshwar said? That we converted hello.c into a form which the processor can understand, but it is still on the hard disk. So if you think about it, so this is your hard disk. So your hello.c is on the hard disk. Your hello is also on the hard disk. So now we are giving the program hello for execution. / means in the current directory. So now when I give this command for execution, the instructions of hello which are present on the hard disk will get loaded to RAM. This is your RAM. I still didn't give the command, but when I give this command, this hello instructions will be loaded. Will be loaded into RAM. When I give the command. And then after that, the CPU which is there, it will start executing the instructions of hello. Your hello program from here, it will be loaded into the memory, and the instructions of the hello will be executed by CPU. No, ASCII, your processor doesn't understand your ASCII encoding. It understands a different language. So it understands the language which your processor understands. We will see. We'll just quickly see. So Balkrishna has this question. I'll answer that later. Are you all with me here that right now the instructions of hello are on the hard disk? And when I give the command and from here to here, GCC helped us out. Okay, GCC helped us out to transform hello.c to hello. Okay, so the moment of truth. So now when you say hello, you can see that hello world got printed here on the screen. This is, yes. So the program got instructions of hello got loaded into the memory, and it got executed, and we are out of the program. So you see that in the output here, after hello world got printed, the prompt came immediately after that. So it's not looking good. So we want to print a new line character. That is, after hello world got printed, we want a new line also to be printed. So we modified the program by adding this /n. Okay, so now let's compile this program again. GCC hello.c -o hello, and then I say dot hello. So now you can see that hello world is printed, and then the new line character is printed, and then the prompt came. I will carry along with, you have all these questions, can we run it on VS Code and all, but I want you to understand some principles. If you just run it in VS Code, you don't understand these principles. /n got printed, Prisha. So earlier there is no new line. So now after hello world got printed, a new line got introduced, and then the prompt came in the next one. And if you see file, what is the type of file? So the type of the file, so it says hello is this file hello, it's an executable file. It's what is in a format called as ELF format. And it uses, you see this thing x86-64, This is the language, this is what is called as the instruction set architecture of the processor. So your source program, instruction set architecture. Your source program got transformed into a sequence of instructions which are specified by this specific instruction set architecture called as x86-64. Yes, that's true. Yeah, that is the instruction set architecture for M1 processor is different. The instruction set architecture for the M1 processor on Mac is different from the Intel processor that I have on my machine. One question at a time. Are you all with me here? Are you all with me here till this point? And now I will show you one more interesting thing. So in order to print a new line, we use this \n, that is what is called as an escape character. You cannot put \n easily in the editor, right? So when you see this is what is called as an escape character. Whenever you have a backslash, this is an escape character for new line. Whenever we want new line, we use backslash. So now I will show you one fun thing, and then after that I will take your questions. So now I'm using a slightly different command, gcc minus capital minus G. Yeah. Load out this minus so obj dump. So don't try to understand everything, just follow me. Your printf, the statement you have, this is the one, this is, you wrote printf statement in the source program, yes or no? Yes, right? And printf statement, your processor doesn't understand printf. Your processor doesn't understand printf. So, but your GCC compiler translates this printf into the sequence of instructions. Don't try to understand the sequence of instructions. And this sequence of instructions is what your processor can understand. Not only that, the sequence of instructions which you are seeing here, LEA, CALLQ, these are human readable instructions, but the actual encoding of them in the binary format is this. So this instruction is encoded like this as a sequence of, this is a what is called as a hexadecimal representation, don't worry about it. But essentially this LEA, it is a sequence of 3, 6, 7 bytes. This instruction is encoded using 7 bytes. And the call queue instruction that you are seeing here, it is encoded using 5 bytes. 5 bytes are used to encode call queue. And this NOP instruction, no op, is encoded using 1 byte. Similarly, pop, this whole instruction, it is encoded using 1 byte. Ret queue is encoded using 1 byte. So if you see here, the printf statement is translated into a sequence of instructions, and all these instructions are encoded as a sequence of bytes. And this is what your processor can understand. So when the processor fetches an instruction And when it looks at 90, it understands it is a no-op instruction. Okay. So like that, the processor fetches an instruction, it decodes the instruction, it looks at the sequence of 5 bytes and it figures out it's a call queue instruction. It decodes and understands the instruction, and finally it executes the instruction. You don't need to remember these instructions, don't worry about it. So this is what happens under the hood. What does the compiler does? The compiler maps your C language statements into a sequence of bytes, into a sequence of instructions which your processor can understand. Are you all with me on this one? Don't look at everything, just focus on what I said, okay? Because otherwise you get confused, because there's a lot going on, but the core idea is this. If you understand, please explain that 90 is not 90. This is a hexadecimal representation which we will learn later. 90 is actually in binary, it is 10010000. This is the binary representation of 90. This is the binary representation of 90. And it is represented in 1 byte. Okay, so it's not 90 actually. This is hexadecimal form, this is binary. Okay, and this is all, this class is very important. I really want you to review this class again and see that you get all the points discussed in today's lecture, because this is foundational thing. So anyway, you will look at these commands. When I post this video, you can look at these commands. The reason why it's good to use Linux for everyone is the commands that you have to use in Windows will be different. But in Mac, it could be the same. So. Okay, so what did you learn? So let's summarize today's lecture. So every program has an input and output. Yes. Program transforms the input or does some computations on the input and generates the output. That's number one. What are the second is we wrote a simple hello.c program. This program is stored. Where is this program stored? Where is this program stored? Hello.c program. Hard disk. Nice. How is it stored? Bytes as a sequence of ASCII characters. Can the processor directly understand this program? No. In order to make the processor understand the program, what do? We compile the program. GCC, we compile the program. GCC hello.c, we compile it. And then an executable gets generated. Where is that executable present? In the hard disk only, not on the RAM, on the hard disk only. And when you execute the program, what will happen? The instructions of the program gets loaded into memory, into RAM, and then the processor executes. And then, so in order to get an insight into what is, this is the language which we understand. This is the tab which we understand, and this is the tab which the processor understands. Okay, especially the processor understands the binary form of this. Okay, like for example, where are we? Hello world, right? So your printf is translated into a sequence of 5 instructions. LEA, call queue, no, these are still, we can read them. The processor doesn't understand them, but the binary encoding of them is given here. And this is what the processor understands, and the processor fetches them, decodes them, and executes them. And this is the summary of today's lecture. Yeah. So now I will stop my lecture here. Are you all happy? There are some small questions here and there, but overall, are you all happy with today's lecture? Good. Okay. So I'll stop recording here.